This is the holography experiment. You're working with an HENE laser. You shine the laser through a beam splitter, and the beam splitter splits the laser into two path lengths. When you look at path length A, it gets put through a lens, which scatters it, hitting onto the mirror, off of the mirror onto the object, and off of the object onto the film. Where the black circle is where the film is. Then there's path length B, so laser beam B gets hit onto a mirror, into a lens, scattered, and then filtered into a pinhole, and then through the pinhole straight onto the film without intersecting the object. These two path lengths have to be equal. The more equal they are, the more focused the image at the end will be. To change the intensities, you have to move this beam splitter left and right in a diagonal way. You have to make sure that beam A is brighter than beam B, because beam A has to bounce off of the object and then hit onto the film, whereas beam B goes straight onto the film. So you want the object, when it's hitting from the mirror onto the object, you want the object to be completely illuminated with light. And when you move it this direction, towards yourself, beam B gets brighter. When you move the beam splitter away from you, beam A gets brighter.
Okay, thank you very much.
So this is the film you'll be working with in the holography experiment. There's two boxes in here, and you can expose the film to the light. So when you're ready to take a picture, everything is aligned, you turn off the light, and in complete darkness, you open the two boxes, take out one of the films, close the boxes, and then you put the film behind this flap. It's stuck on like a magnet. You close the flap, go back, turn on the laser, expose the film for about 10 seconds, turn off the laser, take out the film, and this is still in complete darkness, bring it over to this tank, and this is kind of an example of a film. You put the film right here, and then you put it in the tank, close the tank, and now the tank is completely light-proof. At this point, you can turn on the light. Afterwards, you pour the developer into the tank through this hole, and there's a leak guard, so if you pour too much, it starts overflowing, and at that point you can stop. And you agitate it for about 7 minutes, pour the developer back in the box, using a sink, pour in some water, agitate it for 2 minutes, pour out the water, pour in the fixer next, until, again, it starts either overflowing or, as long as the film is covered, that's the most important thing. Agitate it again for about 7 minutes, pour the fixer back into the bottle, then you pour in water again, you agitate it for 2 more minutes, pour out the water. At this point, you can open the tank and expose the film to the light, at which point you put the film into this tank. And then using gloves and this, you pour bleach onto the film, and you just move the film around, and you make sure that all the black that's on the film disappears, and then you can take the film right out of the tank, rinse it, let it dry, and you have yourself a hologram. And that's it.
So here is the hologram of the R2-D2, following the procedure that I mentioned before. This is with the green light laser.
Yep.
Can we move to the red light laser?
Yes. This is with the red light. There we go. It's not as intense of a laser, so the object is not as bright as the green light.
This is great, thank you.
So right now, we're looking at a single slit interference pattern, which for us is just one single line. And the laser can point all the way to this detector here. And what we can do is we can connect the detector to a voltmeter, and we can observe the voltage that the light is emitting. And the detector actually is connected to this micrometer, so we can change the position of the detector. So we can look at the differing voltage of the single slit pattern as a function of position. And we can do the same thing with the double slit. Can't really see it too well, but it'll split into 2 lines. We have a slit blocker here, so you can either block off one of the slits and just do single, or you can open it up and to do double. and do the exact same thing here with the micrometer and the voltage, and you should see, your typical double slit interference wave pattern.
So this is with the laser, and the idea is that you'll use a very low intensity lamp to then do single photon.
Yeah, to try to do one photon at a time to kind of prove the idea that the photon will be interfering with itself.
Okay.
Because the only way you can get, that pattern.
Okay, thank you.
There's interference.
Yep. Alright, this is the Faraday mutation experiment. We use it to measure the Faraday constant by using an AC magnetic field. This here is the audio amplifier, the laser, solenoid, linear polarizer, photodetector, your oscilloscope to measure the signals, and the lock-in amplifier, which we'll use to measure small signals. So right now in the oscilloscope, we're reading a DC signal from the laser light from this photodetector, and it's approximately 300 millivolts. And on top of this, we have a small AC signal on the order of fractions of a millivolt. And you'll see that. And if we change the attenuation on the audio amplifier, we can see that there is an AC signal, but it's very small, it's very difficult to measure. So what we can do is, if we pass the signal through a preamplifier, and then through a bandpass filter, and then through a lock-in amplifier, the signal becomes much easier to detect. And we chose to use a linear polarizer at 45 degrees to the laser light. This simplifies the situation. If we change the B field, we can take the ratio of the AC signal to the DC signal versus the magnetic field times the length, and this will give us our Faraday constant.
So can you show us how more sensitive you are by changing the magnetic field and looking at your rectified signal?
If we look at the signal coming out of the lock-in amplifier, this is at 0 signal, and this is at maximum signal. If we change the scale, you can see that it's much easier to read.
That's great. Thank you very much.
Hi. Here we're going to look at the noise that you find in electronics. So the first thing we're looking at is Johnson noise, which you find in your resistances. This occurs because of thermal agitation in your electronics. So for this part, we're looking at different resistances so that we can quantify the Johnson noise in each particular resistance. So the first part of it is your low-level electronics. So the only part we're using for the Johnson noise is the preamplifier noise, the low-level electronics for the preamplifier. This gives you the range of the resistances that you're going to measure the noise in. The RF gives you the amplification. In this case, we're going to set a constant amplification of 600 because you have an RF of 1K and another 200 resistor, which gives you a total gain of 600. That is all you're getting from the low-level electronics. Then you connect it to your high-level electronics, where you set up your bandwidth. In this case, we're taking the bandwidth from 0.1K to 100K hertz. From there, you set up the gain from the filters. You can change the you can change the gain depending on the voltage you get from your resistor. From there on, you can now read out your voltage using a digital multimeter. And you also have to take care to set this gain so that you're within the linear range, because the resistance at high resistances for like 100K ohms, the dependence on the voltage is no longer linear. So you have to remain within 0.6 to 0.1 of your volts so that you're at the linear range. So we're going to start with, for example, 100 ohms. From there you can read out the value for your voltages. And a thing to note is that because of the amplification from the high level electronics, you have some contribution of noise from the high level electronics amplification. So to quantify that, once you get your noise for each of the resistances, you can plot out a linear plot. You get out a linear plot. This is just a schematic. And where you have your y-intercept, that is the quantity in which you have noise contribution from your amplifier section from the high level electronics, and you have to subtract it out of your total noise to get the actual Johnson noise.
And so what fundamental constant can you measure from this?
Right. So since you can relate your Johnson noise to the resistance and to your bandwidth, and this is how you relate your Johnson noise. You have your Johnson noise as a function of your Boltzmann constants, your temperature, your resistance, and your bandwidth. And using this, if you plot out your line, you're able to extrapolate the Boltzmann constant from the Johnson noise. So it isn't totally a bad thing to have Johnson noise.
Thank you very much.
This is the Michelson setup. You have a laser bouncing off mirrors going through a beam splitter, and the fringes are being detected by a photodetector, which is attached by this instrument, which counts the fringes as they move. And you have a motor pressing against this mirror, which makes the fringes move. So if I turn on the motor and I reset the counter, you could actually see how the fringes are being counted. It's a very sensitive instrument, so actually if I even tap on the table, it moves the fringes. So you have to make sure that when the fringes are counting, you're not moving around or putting anything on the table.
So how does this relate to a physical property?
As the fringes are moving, you take the distance that the number of fringes moved, divide it over the distance that the micrometer moves, multiply it by 2 because the beam goes 2 path lengths, and you get the wavelength of the light that you're using.
Okay. And what are we hoping to see here?
We're hoping to see the shifting of the fringes. It's kind of like a reflection, one of the reflections that we're able to see.
Okay.
Signal has to be at before it gets counted. And so this uses photon statistics. And right now I'm about to check my data for the double slit interference pattern to see if it matches.
So you're seeing counts at the moment. What counts are these that we're seeing on the...
These are counts of noise because the shutter's closed.
Can
It's
we
not picking up the actual signal, it's just picking up whatever it picks up because of the high voltage.
can we open the detector and see what counts we'd get?
Sure.
And where are you on where do you expect you are on the pattern? You're on the what sort of point? The central
Right
maximum?
now it's set to the maximum according to my double slit data
of the
For the bulb.
laser
for the bulb.
for the bulb.
The
Okay.
laser had a different maximum point.
Okay. And can we just move slightly off to see how the count rate changes? So at the moment we got 1100 counts,
Oh, oops.
and then we can just move slightly off.
I moved it from 5 to 25 on the small one.
Okay.
Should be a significant difference. It counts for 10 seconds here.
So we got half as many counts essentially.
Yeah, roughly.
Okay. Thank you very much.
Well, this is the Zeeman effect, which is the splitting of the spectral lines of whatever your sample is. In this case, it's mercury. Well, what happens here is we translate the energy differences of these sublevels of these energy transitions into differences in wavelengths because of the epsilon. As the light passes through, some of it is transmitted, but some of it is kept. So it creates some constructive and deconstructive interference. And these wavelengths, we have them transferring into an interference pattern, which is shown here.
So what is the Zeeman splitting aspect of what we're seeing here?
Well, if the B field was not present, you wouldn't see these multiple lines, but it is, and that's due to the angular momentum, well, the total angular momentum of your sample, which in this case is contributed by the orbital angular momentum and the spin angular momentum, and due to some selection rules, the electrodipolar transitions, certain transitions are possible, and the one quantum number that you're interested in is the magnetic quantum number, and that the values that you can get that is determined by your J values, which range from -J up to J.
Okay, thank you very much.